Hello and welcome to our Mathematics IV course, which is a course about differential equations. Today I'm going to start with some information about the course, and then I'm going to cover the first 4 topics. An introduction, some simple examples. I'm going to teach you how to draw a direction field, and then we'll look at how to solve the examples that we set in section 1.2. I'm expecting to give 12 classes to you. They will be on Thursday afternoons between 4 and 6. My teaching style is, first I'm going to give you a lecture, and it will be roughly 60 minutes, although that will vary week by week. And then after the lecture is finished, I'll be available to answer your questions about this week's lesson, or about previous topics, or about the exams, or whatever you want. If you don't have an hour's worth of questions, then we can finish early, that's fine. I said the lesson would be roughly 60 minutes, but that will vary. Some weeks I might be a little bit longer than 60 minutes. Some weeks I'll be shorter than 60 minutes. We can break the topics in this course up into 5 parts. The first is the introduction. I'll explain what is a differential equation. I'll give you some examples. I'll teach you about direction fields and classifying differential equations. In part 2, we'll be talking about first order differential equations. Then we'll look at second and higher order linear differential equations. We will look at the Laplace transform and how to use that to solve differential equations. And then in the final section, we'll use some linear algebra to look at systems of first order linear equations. So I'm going to use the first 3 lectures to cover the first 2 parts, and then after that there'll be 3 lectures for each part. Because I'm breaking it up like this is why some lessons will be more than 60 minutes and some will be shorter than 60 minutes. I've written lecture notes for this course. You can find this in the course material section. And we're going to examine this course with 3 exams. There will be 2 midterm exams and 1 final exam. And I'm expecting them to be, the midterm exams to be worth 20% each, and the final exam to be worth 60%. And I'm expecting that these will be classroom exams. First one I'm expecting to be in the 8th week of term, second midterm exam perhaps in the 12th week, and then the final exam after the end of course. There's no homework this semester, it's just exams for this course. Information on this slide might change depending on what the university decides, what happens over the next term. So I'll let you know nearer the time what we're doing. If this was a classroom course, then you would have 4 hours of lectures every week. And the general rule of thumb is that for each hour of lecture you have, you're expected to study another 1 to 2 hours outside of class. So we can think of this course as somewhere between 8 and 12 hours of study each week for you. For an online course, still we're expecting you to study somewhere between 8 and 12 hours each week, but because we'll only have 2 hours scheduled in class, that means you're expected to study somewhere between 6 and 10 hours by yourself each week. What can you be doing in this time? You could be rewatching the lectures. These will be recorded and then made available on both OLearn and on YouTube. You can read the lecture notes or the slides which I'm making available to you. There's lots of exercises in the lecture notes, and most of them have answers in the back. So you can sit and try to solve these problems, and then you can check the answers at the back to see if you're understanding it correctly. There's a discussion board in Olearn in which you can talk to other students. Feel free to help each other understanding the material or help each other with the exercises in the lecture notes. Or you can ask questions to me on the discussion board. You might like to read books about differential equation. I'm going to recommend two good books. Or you might want to spend your time watching online videos by other teachers about differential equations. Two books which I recommend for this course. Boyce, DePrima and Mead have a good book called Boyce's Elementary Differential Equations and Boundary Value Problems, which is published by Wiley. This is the book which I've used to plan this course. If you want a book which is like the lectures, like the lecture notes, but with more detail, then this is the book to get. The second book I recommend is by Edwards and Penny, and it's called Elementary Differential Equations with Boundary Value Problems. If you want a book which explains things in a different way from me, then I suggest you pick this book. These books are optional. You don't have to buy them. You might find them useful, but you don't have to buy these if you don't want to, because there's no homework for this course. And before we begin, let me just point out, in the bottom left corner, I have the slide number. This will give you a rough idea as to how far I am through the lecture. And if you're following along on the lecture notes, I'm writing the section title at the top. Okay, let's start with an introduction to differential equations. If I said solve x plus 3 is equal to 5, then I'm asking you to find a number x which satisfies this equation. But if I said solve dy dx is equal to 2x, then this time I don't want a number. This time I want you to tell me a function y of x which satisfies this equation. This second equation is a differential equation. A differential equation is just an equation which has a derivative in it. This is an equation. In this equation, there's a derivative, so this is called a differential equation. For example, solve dy dx is equal to 2x. I want a function y of x such that when we differentiate it, we get the function 2x. And this equation is quite easy to solve. We just write that y is the integral of the derivative of y, because if we differentiate a function and then we integrate it, we get back to where we started from. So integral of 2x is just x squared plus c. The solution to this differential equation is y is equal to x squared plus c. Or I might give you problems like this. Solve dy dx is equal to 2x with another condition, with the condition that y of 0 is equal to 5. In this problem, we have two conditions. The first line, dy dx equal to 2x, is a differential equation. The second line, which says that we must also have that y of 0 is equal to 5, is called an initial condition. And altogether, the problem is called an initial value problem, or IVP. The whole problem, the differential equation and the initial condition together, is called an IVP, or initial value problem. So we know the solution to the differential equation. We've just seen that that's y is equal to x squared plus c. We need to choose the value of c which satisfies the initial condition. So we start by writing 5 is equal to y of 0. That's our initial condition. We know that y of x is x squared plus c, so y of 0 must be 0 squared plus c. And from this, we can see that we must have that c is equal to 5. So the solution to the initial value problem must be y is equal to x squared plus 5. Let's do another one, another initial value problem. We have the differential equation, dy dx is equal to sine x, and the initial condition, y of 0 is equal to 3. First, we're going to solve the differential equation, and then we're going to choose the correct value of c to satisfy the initial condition. So, just as we did the previous time, y is the integral of the derivative of y. Integral of sine, of course, is just minus cos x plus c. And then we take the initial condition, write this backwards, right? 3 is equal to y of 0. Y of 0 must be minus sine 0 plus c. And then we can see that we must have that c is equal to 4. So the solution to the initial value problem is minus cos x plus 4. Solve dy dx is equal to y. Now this is different. Now the right-hand side is not just a function of x. Now we have y appearing. We can't just do what we did before. We can't just integrate dy dx to find y of x. We're going to need to use a different method to solve this differential equation. And I'm going to show you how to solve this later today. First, I want to look at some examples of differential equations. Many problems in engineering or science or social sciences can be modeled using differential equations. I'm going to start with 3 simple examples. First example, imagine we have a falling object. Let's suppose we have an object of mass 10 kilograms, and imagine this object is falling downwards. The velocity of this object I'm going to call v of t, and downwards is going to be the positive direction. What forces are acting on this object? There's gravity and there's drag. The gravity is pointing in the same direction as the velocity, so the gravity will try to make the object go faster and faster. Drag is pointing in the opposite direction from velocity, so the drag will try to slow the object down. We need units before we can go any further. For velocity, I'm going to use the units meters per second, and for time, I'm going to use seconds. Newton's second law says force is equal to mass times acceleration. The mass is 10 kilograms, and the acceleration is the derivative of the velocity. So 10 dv dt. Now note, velocity is measured in meters per second. Time is measured in seconds. So acceleration is going to be measured in meters per second divided by seconds, or meters per second squared. Now, what are the forces? We have gravity. This is positive force because it's pointing in the same direction as velocity, and drag, which will be a negative number because it's pointing in the opposite direction from velocity. On the Earth, the gravity of an object of mass 10 kilograms is approximately 10 g, where g is the constant, 9.8 meters per second squared. it's reasonable to assume, as long as the object isn't traveling too quickly, that drag is proportional to velocity. We have a symbol for is proportional to, it's this symbol here. And what this means is that drag is equal to some constant multiplied by velocity, where our constant gamma is a positive number which depends on the shape of the object. What does that mean? That means if we have a streamlined object, we'd expect the number gamma to be a small number. If we have something like a parachute, which is not streamlined at all, we'd expect lots of drag. We'd expect our constant gamma to be a big number. For this example, let's choose a nice easy number. Let's suppose for our object, gamma is 2 kilograms per second. So mass times acceleration, that's 10 dv dt, is equal to the force, gravity minus drag. Gravity, we've said, was 10g, or 98, and drag is gamma v. So we have minus 2v. Divide both sides by 10, and we get the differential equation. dv dt is 9.8 minus v over 5. This is our differential equation for the falling object. We're going to solve this equation later, but first I want to look at this differential equation's direction field to try to understand how solutions are behaving. A direction field is just a grid of arrows, in this case in the TV plane, which shows the slope of solutions to the differential equation at different points. The direction field to this differential equation looks like this. After we have our direction field, we can make some guesses at what the solutions look like. Let's suppose we start at, let's say, 54. So I'm going to start just here. The arrow is pointing downwards, so the solution should go down with this slope. The next arrow we get to is also pointing down, but not quite as steep. So we expect we have to go down this way. And we keep going. The arrows are pointing downwards, but the slope is tending to 0. So I'm expecting a solution to look like this. Let's replace this with one generated by the computer. Let's make some more guesses. If we started at 60, say, the solution should look like this. Just follow the directions that the arrows are pointing. If we started at minus 40, so at 42, the arrow is pointing upwards, so we'd expect the solution to go upwards. And then we keep following the way that the arrows are pointing. We can guess that the solution looks something like this, or we can use a computer to generate the solution to see how good my picture was. This is the true solution. And so on. You can keep making guesses at how the solutions look. You'll notice that somewhere in the middle, in this case at 49, there should be a constant or equilibrium solution. Note that if v is 49, then dv dt is 9.8 minus v over 5, 9.8 minus 9.8, or 0. So the slope is always 0. In other words, v equal to 49 is a constant solution, or an equilibrium solution. Let's look at our second of these 3 examples. Now let's talk about a population of mice in a particular area. Now the time t is going to be measured in months. we can assume that there's plenty of food for the mice to eat. So as long as nothing eats the mice, as long as nothing kills the mice, we would expect our population to increase at a rate proportional to p. In other words, we'd expect dp dt to be proportional to p, or dp dt to be equal to some constant rp, where r is a positive number. And just to make this easy, let's put a number in. Let's suppose that our constant r is 0.5 per month. So far we've got the differential equation dp dt is equal to p over 2. However, I said that was if nothing eats the mice. Let's suppose that 5 owls also live in this area, and let's suppose that each owl eats 3 mice each day. So I'm saying 1 owl eats 3 mice per day. In total, the 5 owls eat 15 mice each day. And if we assume there's 30 days in a month, the owls are eating 450 mice each month. We can include this in our differential equation. We can add minus 450 to the differential equation. You should think of the p over 2 as how many baby mice are born each month, and the minus 450 as how many mice die each month. Then dp dt is the number of baby mice born minus the number of mice which die. Let's look at a direction field for this differential equation. It looks something like this. Again, we can make some guesses at the solutions. If I start just here at 902, the arrow is pointing upwards. Follow the arrows, we'd expect a solution to look something like this, and so on. I guess there's a solution here, I guess there's a solution here, and so on. Let me use a computer to show you some real solutions to the differential equation. These orange curves are solutions to equations. We could guess that they look like this just from looking at the arrows. Example number 3. This example is about a cup of coffee. Newton's law of cooling states that the temperature of an object changes at a rate proportional to the difference between its temperature and the temperature of its surroundings. Suppose that the temperature of your cup of coffee obeys Newton's law of cooling. Suppose that it has a temperature of 90 degrees when you make it, and suppose that the temperature of your room is 20 degrees. Write a differential equation for the temperature of your coffee. Okay, now we can expect that the coffee cools something like this. At the start, when the coffee is very hot, we'd expect the temperature of the coffee to cool quite quickly. But when the temperature of the coffee is just a little bit above the temperature of the room, we'd expect the temperature of the coffee to cool more slowly. So we'd expect to have some sort of curve like this. This is what Newton's law of cooling says. Let kT denote the temperature of your coffee in degrees Celsius, and let T denote time, and this time let's say time in minutes. Newton's law of cooling tells us that dk dt, the rate of change of the temperature of the coffee, is proportional to the difference between the temperature of the coffee, which is K, and the temperature of the room, which is 20. So we expect to have the differential equation dk dt is equal to some number r multiplied by 20 minus k. Is k a positive number? Sorry, is r a positive number or is r a negative number? hot coffee cools down, and if instead we made some very cold coffee, some iced coffee, we'd expect that to warm up. So we would need to have the R as a positive constant. Let's talk about direction fields. How can we draw a direction field? First of all, what does slope mean? Think about the graphs y is equal to mx for different values of m. I've drawn a few here. Y is 0, y is a half x, y is x, y is 2x, y is 4x, etc., etc. Looking at y is equal to 2x first, this is a graph with slope 2. Anytime we're thinking of something with slope 2, we're thinking of a line which slopes up like this. When we draw a direction field, we're going to be drawing lots of little arrows, and we're going to be drawing them with these slopes. If we find, I'm looking at the orange one first, if we find that we want dy is equal to 2, we're going to draw a little arrow with the same slope as y is equal to 2x. If we find, and let's say the pink one, if we find that dy dx is equal to -1, we're going to be drawing a little arrow which slopes downwards with slope -1. Okay, so draw a direction field for the differential equation dy dx is equal to x plus y. I'm going to start with an empty grid and a table. First, I'm going to calculate the derivative at 10 points, and I'm going to draw those 10 arrows. First of all, let's look at the point 0, 0. Put x is 0 and y is 0 into the equation. 0 plus 0 is 0. At this point, dy dx is equal to 0. To show this on the graph, we draw a horizontal arrow. Next point, point 1, 0. Put x equal to 1 and y equal to 0 into the equation. dy dx is equal to 1 plus 0, or 1. When the slope is equal to 1, we draw an arrow which slopes upwards with slope 1. So we're going to draw a little arrow like this, and so on. At the point 2, 0, the slope is equal to 2. So again, the arrow is pointing upwards, but it's sloping up more than the previous one. At -1, 0, x plus y is equal to -1, where we draw an arrow sloping downwards, and so on. At, for example, the point -1, -1, I do x plus y, and I calculate -2. So at the point -1, -1, I'm drawing a little arrow which is sloping downwards with slope -2. Let me clear the screen up a little bit. I've calculated 10 points. I want to draw 121 arrows here, because I have 11 dots multiplied by 11 dots. I have 121 dots here. I don't want to calculate the derivative at all of the other 111 points. I want a shortcut. And the shortcut is we're going to look for some patterns, and then we're going to make some guesses. So, for example, look along this line. These 3 arrows are all horizontal arrows. The derivative is always 0 at these 3 points. It's reasonable to guess that all of the arrows on this line are the same. So let's make this guess. Let's fill these in. That saves a bit of time. What about on a horizontal arrow line? Let's say this one. What happens to the arrows as we move from the left to the right? These arrows seem to be rotating anti-clockwise. So it's reasonable to guess that That always happens. All of the arrows on this line should be rotating anti-clockwise as we move from the left to the right. So we can guess that the arrows look like this. We can also look at a vertical line. As we go from the bottom to the top, these arrows are also rotating anti-clockwise. So let's make another guess. Let's guess that this pattern is always true. Let's guess that the arrows look like this. And then keep making guesses. Keep looking at horizontal lines, keep looking at vertical lines, and if possible, look at diagonal lines. Quite quickly, we can fill in all of the arrows. And we get something like this. This is a direction field for dy dx is equal to x plus y. One more example. Draw a direction field for dy dx is equal to xy. If you're re-watching this video, I encourage you to pause the video now and try to draw this yourself. I'm just going to show you the answer. Use the method that I showed you in the previous example. Calculate the arrows at a few points and then make some guesses, and we find that the direction field looks like this. Draw a direction field for dy dx is equal to y multiplied by x plus y. Again, if you're re-watching the video, pause it now and try to draw this yourself. The answer is this. Our final section for today, I want to solve our first differential equations. In particular, I want to look at the falling object equation and the mice and owls equation. The falling object equation was dv dt is equal to 9.8 minus v over 5. The mice and owls equation was dp dt is equal to p over 2 minus 450. Both of these equations are of the same form. They both look like dy dt is equal to ay minus b, where a and b are numbers and y is our function t. In this section, I'm going to show you how to solve differential equations like this. Let's do the mice and owls equation first. dp dt is p over 2 minus 450. It's easier to solve if I write this as p minus 900 all divided by 2. Now, what I'm going to do is I'm going to rearrange this. P minus 900, we can divide both sides by p minus 900, and that would move this over to 1 divided by p minus 900 on the left. And then I'm going to multiply both sides by dt. And what that does is that moves the dt up to the right. As long as p is not 900, we can rearrange this equation so that it looks like dp divided by p minus 900 is equal to half dt. What we're doing here is we're separating the variables. All of the p variables are on the left of the equal sign. All of the t variables are on the right. If we can do this, if we can separate the variables like this, so that all of one variable is on the left and all of the other variables on the right, then we're allowed to integrate the equation. Now, before I go on, of course, dp over dt does not really mean dp divided by dt. It means the derivative of p with respect to t. And if we use the method which I'm showing you now, this annoys pure mathematicians a bit, but this method does work. So as I was saying, if we can separate the variables like this, if we can move all of the p terms to the left and all of the t terms to the right, then we're allowed to integrate our equation. We can write an integral sign on both sides, and it's still true. Integral of a half, straightforward, a half t. Integral of 1 divided by p minus 900 is the natural logarithm of the absolute value of p minus 900. And of course, we need a constant of integration. Yes, we're doing two integrals, but we only need one constant because we could combine them together if we wanted to. So just a plus k on the right-hand side. Now I want to rearrange this to find a formula for p. The first thing I can do is I can take e of both sides. So I'm going to write e of the natural logarithm of the absolute value of p minus 900, which is just the absolute value of p minus 900. And then on the right-hand side, e of, or e to the power of t over 2 plus k. To get rid of the absolute value signs, you can add in a plus or minus. And then we can take the 900 over to the right to get 900 plus or minus e to the power k, e to the power t over 2. Now we can simplify this a little bit further. K is a constant. K is a number that we don't know. So what is e to the power k? E to the power k is some number that we don't know. So plus or minus e to the power k is some number that we don't know. We can use a different notation for this. This is just some number we don't know. We can give this a new name. For example, we can say, let small c be plus or minus e to the power k. Then small c represents the number that we don't know. Then we could write that p of t is 900 plus c e to the power t over 2. And this is the solution to the mice and owls equation. Now let's do the same thing for the falling object equation. dv dt is 9.8 minus v over 5. We're going to do the same method. We're going to separate the variables. We're going to move all of the v terms to the left and all of the t terms to the right. Then we're going to integrate both sides, and then we're going to rearrange to solve for v. And the calculation looks like this. Just have a look through this before I talk about it. Okay, so what I'm doing is I'm starting with a differential equation. It's easier to rearrange if we move everything over 5. So instead of 9.8, I'm changing this to 49 divided by 5, because 49 divided by 5 is 9.8. And then I'm rearranging it so that I'm moving the v minus 49 over to the left. I'm moving the dt up to the right-hand side, and I'm going to leave a minus sign just here. Why am I leaving a minus sign just here? It's because when I integrate, I want to have a 1v just here. Just makes this integral just a little bit easier than if we had a minus v. So now all of the v terms are on the left and all of the t terms are on the right. If we can do this, and only if we can do this, we're allowed to integrate both sides. The left side becomes the natural logarithm of the absolute value of v minus 49, and the right-hand side becomes minus t over 5 plus k. Take the exponential function of both sides. We can remove the absolute value signs as long as we add in a plus or minus somewhere. And then instead of this unknown number, plus or minus e to the power k, we can give this a new name. We can call this small c. We have the solution v is equal to 49 plus c e to the power minus t over 5. And that is the end of this week's lesson. First week was a short lesson. Future weeks, lessons will be roughly 60 minutes long. Next week, we're going to finish talking about chapter 1. We'll talk about classification of differential equations, linear, non-linear, first order, second order, etc. I'll explain what those mean. And then we'll start talking about first order equations. We'll cover linear first order equations, separable first order equations, which is similar to what we've just talked about in the last section. And then we'll discuss some differences between linear and non-linear first order equations. Now, I'm ready to answer your questions now, if you have any about today's lesson. The way my lessons work is, as soon as I get to this final orange slide, you're welcome to stay and answer questions to me, or you're welcome to leave if you wish. I showed you how to solve dy dx. If I go back a few slides to the start of this final section, you find it. I've showed you how to solve dy dt is equal to ay minus b for any numbers a and b. So if, say, we had b equal to 0 and we had a equal to 1, we could use the same method to solve this equation. But the current plan is that the exams will be face-to-face. If this changes near the time, I'll tell you. But for the time being, you should assume that your exams will be face-to-face exams.